Hi everyone, today we're doing notes on 6.5, the central limit theorem. So first we have to talk about the theorem for a normal probability distribution. This says, let x be a random variable with a normal distribution whose mean is x bar and whose standard deviation is sigma. Let x bar be the sample mean corresponding to random samples of size n taken from the x distribution. Then the following is true. The x bar distribution is a normal distribution. The mean of the x bar distribution is mu. So we can say mu of x bar equals mu. The standard deviation of the x bar distribution is sigma divided by square root of n. So sigma x bar is equal to sigma divided by square root of n. Suppose a team of biologists has been studying the Pinedale Children's Fishing Pond. Let x represent the length of a single trout taken at random from the pond. This group of biologists has determined that x has a normal distribution with a mean of 10.2 inches and standard deviation sigma of 1.4 inches. What's the probability that a single trout taken at random from the pond is between 8 and 12 inches long? So we'd say the probability that 8 is less than or equal to x less than or equal to 12 is equal to, we can use normal CDF. Lower bound is 8, upper bound is 12, mean is 10.2, standard deviation is 1.4, and that's going to give us 0.8427. What is the probability that the mean length x bar of 5 trout taken at random is between 8 and 12 inches? So now we're dealing with 5 trout, not a single trout, so we need to find our new mean and standard deviation. So our mu of x bar is equal to mu, so this is still 10.2. But our sigma of x bar is equal to sigma divided by square root of n. So this is 1.4 divided by the square root of 5, which this is going to give us 0.6261. So now we're going to do normal CDF. Lower bound is 8. Upper bound is 12. Mean is 10.2. Our new standard deviation is 0.6261, and that's going to give us 0.9978. Looking at the results of parts A and B, we see that the probabilities, now these were done using the chart, so that's why these are off by a tiny bit, are quite different. Why is this the case? So one trout, we have our sigma is 1.4. 5 trout, the mean of those 5, has a sigma that is 0.6261. So if we're thinking about this, looking at the chart, right? So if I wanted to make a graph, I'm going to erase this. If I'm making my graph for one trout, it's going to look like this, right? We have a mean of 10.2, one standard deviation, we have 1.4. So one standard deviation away, this is about 8.8, and this is about 11.6. Now, if I do the smaller standard deviation, I'll do this one in purple. This one is going to look more like this shape, right? It has a much smaller standard deviation. So that smaller standard deviation means we have more trout in the range that we're talking about. Okay, standard error. So standard error, this is the standard deviation of a sampling distribution. So those words can be used interchangeably. So for the x bar sampling distribution, the standard error is sigma divided by square root of n. Our central limit theorem, this says if x possesses any distribution with a mean mu and standard deviation sigma, then the sample mean x bar based on a random sample of size n will have a distribution that approaches the distribution of a normal random variable with mean mu and standard deviation sigma divided by square root of n as n increases without limit. So the key here is that your n has to be greater than or equal to 30 in order for it to approach a normal distribution. Okay, so again, n must be 30 or larger when symmetrical about the mean. If it lacks symmetry, a sample size larger than 30 may be necessary. Why do we use this? It's used when you don't have information about the shape of the original x distribution. As the sample size gets larger and larger, the distribution of x bar will approach a normal distribution. What does the central limit theorem tell us? When n is greater than or equal to 30 in most cases, it tells us that the x bar distribution is approximately normal. The mean of the x bar distribution is mu, the mean of the original x distribution. And the standard deviation, also known as the standard error of the x bar distribution, is sigma divided by square root of n, where sigma is the standard deviation of the x distribution. So here's an example that's similar. Suppose that the waiting times at a checkout of a grocery store have a mean of 2.7 minutes and a standard deviation of sigma is 0.6 minutes, okay? It doesn't say that they're normally distributed. So it says, can we use the methods of this section to find the probability that the average waiting time of a sample of 10 customers is between 3 and 4 minutes? So this is no, because we don't know anything about the shape, and here our n is 10. So that's less than 30. Again, keep in mind, in order to assume it's normally distributed, your n has to be greater than or equal to 30. What's the probability that the mean of a sample of 30 waiting times is between 3 and 4 minutes? Well, since our n is 30, we can use our central limit theorem. So if we do this, we're looking for our probability that our x is between 3 and 4. We have our mean. Here's our standard deviation, right? We calculated our new one. So this is what it looks like using our z-score in the chart. You can also do normal CDF of 3 lower bound, 4 upper bound. Again, this is what we're finding here. Our mean is 2.7 and our new sigma x bar is going to be 0.1095, and that comes out to give us 0.0031. Same as if you use the chart. Okay, so here's another practice. Suppose x has a normal distribution with a mean of 18 and a standard deviation sigma is 13. If you draw random samples of size 5 from the x distribution and x bar represents the sample mean, what can you say about the x bar distribution? How could you standardize the x bar distribution? So again, we're told that x has a normal distribution, so we don't need to worry about that sample size being greater than 30, right? We have a sample size 5, which is fine because we know it's normally distributed. So our mu of x bar is equal to mu, so that's 18. Our sigma of x bar is equal to sigma divided by square root of n, which gives us 13 divided by square root of 5, which is 5.81. And again, when x is normally distributed, the x bar distribution will also be normal. Okay, so suppose you know that the x distribution has a mean mu of 75 and a standard deviation sigma of 12, but you have no information as to whether or not the x distribution is normal. If you draw samples of size 30 from the x distribution and x bar represents the sample mean, what can you say about the x distribution? How could you standardize the x bar distribution? So our n is equal to 30, which is greater than or equal to 30, so we are okay. So our x bar distribution will be normally approximated. Our mu of x bar is equal to our mu, which in this case is 75. Our sigma of x bar equals our sigma divided by root n, which is 12 divided by root 30, and that's going to give us 2.19. Suppose you did not know that x had a normal distribution. Would you be justified in saying that the x bar distribution is approximately normal if the sample size were n equals 8? So here, this is less than 30, right? So no, if we do not have a normal distribution, for x, we need a sample size of n is greater than or equal to 30 to approximate normality for the x bar distribution. Okay. A certain strain of bacteria occurs in all raw milk. Let X be the bacteria count per milliliter of milk, of milk. The health department has found that if the milk is not contaminated, then X has a distribution that is more or less mound shape and symmetric. The mean of the X distribution is mu equals 2,500, and the standard deviation is sigma equals 300. In a large commercial dairy, the health inspector takes random samples of the milk produced each day. At the end of the day, the bacteria count in each of the 42 samples is averaged to obtain the sample mean bacteria count X bar. Assuming the milk is not contaminated, what is the distribution of X bar? Meaning, please find the mean and standard deviation. So our mu of X bar is equal to mu, so this is 2,500. Our sigma of X bar is equal to sigma divided by square root of n, so this is 300 divided by square root of 42, which comes out to 46.29. Assuming the milk is not contaminated, what is the probability that the average bacteria count X bar for one day is between 2,350 and 2,650 bacteria per milliliter? Please find this. So we're looking for our probability that our X is between 2,350 and 2,650. So we can do this as normal CDF. Lower bound is 2,350. Upper bound is 2,650. Our mean is 2,500, and our standard deviation is 46.29. So this comes out to give us 0.9988. At the end of each day, the inspector must decide to accept or reject the accumulated milk that has been held in cold storage awaiting shipment. Suppose the 42 samples taken by the inspector have a mean bacteria count X bar that is not between 2,350 and 2,650. If you were the inspector, what would be your comment on this situation? So I would say that the probability that it's contaminated is very high, because we had 0.9988 or 99.88% probability that it's between that range. So if it's not in that range, it's most likely contaminated. All right, so how to find probabilities regarding X bar. So probability distribution of X values, where n is the sample size, mu is the mean, sigma is the standard deviation. If the X distribution is normal, then the X bar distribution is normal. Even if the X distribution is not normal, if the sample size is greater than or equal to 30, then by the central limit theorem, the X bar distribution is approximately normal. So we convert our X bar to Z using the formula. Okay, so once you can do it this way using the Z-score and then use the standard normal distribution. Another thing you could do is once you find your mu of X bar, which is mu, and your sigma of X bar, which is sigma divided by root n, you can also use normal CDF, where then we're putting in our lower bound, upper bound, mean of X bar, and our sigma of X bar. Okay, so here is another problem. In mountain country, major highways sometimes use tunnels instead of long winding roads over high passes. However, too many vehicles in a tunnel at the same time can cause a hazardous situation. Traffic engineers are studying a long tunnel in Colorado. If X represents the time for a vehicle to go through the tunnel, it is known that the X distribution has a mean of 12.1 minutes and a standard deviation sigma 3.8 minutes under ordinary traffic conditions. From a histogram of X values, it was found that the X distribution is mound-shaped with some symmetry about the mean. So basically, we know that it could be approximately normal because it's mound-shaped and some symmetry. Engineers have calculated that on average, vehicles should spend from 10 to 13 minutes in the tunnel. If the time is less than 11 minutes, traffic is moving too fast for safe travel in the tunnel. If the time is more than 13 minutes, there is a problem of bad air quality or too much carbon monoxide and other pollutants. Under ordinary conditions, there are about 50 vehicles in the tunnel at one time. What is the probability that the mean time for 50 vehicles in the tunnel will be from 11 to 13 minutes? So let X represent the sample mean based on samples of size 50. Describe the X bar distribution. So again, our N is 50. So our mu of X bar is equal to mu, which is 12.1. Our sigma of X bar is equal to sigma divided by root n, which is equal to 3.8 divided by square root of 50. So this is 0.5374. We know our X bar is approximately normal because our X is approximately normal. And we have that our N is 50, which is greater than or equal to 30. All right, for B, we have to find the probability that our X bar is between 11 and 13. Please do this. So we're looking for our probability, 11 less than or equal to X bar, less than or equal to our 13. And so this is going to be normal. CDF, lower bound is 11, upper bound is 13, mean is 12.1, standard deviation is 0.5374. And so when we calculate this, we get 0.9327. Interpret your answer to part B. Well, this basically says that 93% of the time, there should be no safety hazard. All right. Here's a question about impulse buying. Let X represent the dollar amount spent on supermarket impulse buying in a 10-minute unplanned shopping interval. Based on a Denver Post article, the mean of the X distribution is about $20, and the estimated standard deviation is about $7. Consider a random sample of N equals 100 customers. each of whom has 10 minutes of unplanned shopping in a supermarket. From the central limit theorem, what can you say about the probability distribution of X bar, the average amount spent by these customers due to impulse buying? What are the mean and standard deviation of the X bar distribution? Is it necessary to make any assumption about the X distribution? Explain. So please find the mean and standard deviation here. So our mu of X bar is mu, which is 20. Our sigma of X bar is sigma divided by root n, which is 7 over root 100, or 7 over 10, which is 0.7. And we can say the distribution of X bar is approximately normal because our n is equal to 100, which is greater than or equal to 30. So now what's the probability that X bar is between $18 and $22? Please find this. So here we have the probability 18 less than or equal to X bar less than or equal to 22. So this is normal CDF of 18, 22, 20, and 0.7. And this comes out to give us 0.9957. Now keep in mind, this is a probability that X bar is between 18 and 22. So this is talking about our sample mean of 100. Let us assume that X now has a distribution that's approximately normal. What's the probability that X is between 18 and 22? So because we're just looking at X here, this is a sample of 1. Okay, so we're back to our mu is 20 and our sigma is 7. I want you to find this one now. So here, again, our probability X is between 18 and 22. Again, we're doing X now, not X bar. So this is normal CDF, 18, 22. Our mean is 20. Our standard deviation is 7 from the original problem because we're just looking at a sample of size 1. So this is 0.2249. So in part B, we used X bar, the average amount spent, computed for 100 customers. In part C, we used X, the amount spent by only 1 customer. The answers to parts B and C are very different. Why would this happen? In this example, X bar is a much more predictable or reliable statistic than X. Consider that almost all marketing strategies and sales pitches are designed for the average customer and not the individual customer. Again, B, this is really looking at our average, right? Individual is when we looked at C. So how does the central limit theorem tell us that the average customer is much more predictable than the individual customer? So individuals may vary from not ever impulse buying to large spending on impulse buying. So the more people evaluated, the more likely there will be some sort of average amount spent impulsively. And that's where we're going to stop today.